Hello everyone, my name is Qingqing Ye from Renmin University of China. Today I'm going to present our work on graph metric estimation with local differential privacy. It is a joint work of Renmin University of China, Hong Kong Polytechnic University, and National University of Singapore. In this talk, I will first introduce some research background and our motivation. Then I will present the problem statement and give our practical solution. In 2018, Facebook privacy scandal was brought into sharp focus all over the world. In that scandal, Facebook exposed the personal profile of 87 million users to Cambridge Analytica, and the latter used the Facebook data to understand and target voters. The main cause is that Facebook allows these apps to access the friend list of a user, which helps to propagate these apps easily through friends. From this scandal, we may know that while providing graph analysis service, it is important to safeguard graph data of individuals, but a centralized data collection may not be trusted. Nowadays, graph analysis has received great attention. In this table, we list some of the most popular graph analysis tasks, like synthetic graph generation, community detection, page rank, and connectivity analysis task. For each of them, a certain graph metric will be considered. For example, clustering coefficient is a necessary graph metric for synthetic graph generation. From the derivation of these graph metrics, we may know all of them can be derived from adjacency bit vector and node degree of a user node. In many real-world applications, graph data comes from individual users. For example, each node in Facebook data is a Facebook user, so privacy protection should be considered. For privacy-preserving graph metric estimation, there are two solution paradigms. The first one is generating a synthetic graph to calculate different kinds of graph metrics. Under this paradigm, for an original graph, some graph statistics, such as node degree distribution, will be sent to the data collector. Then, by using some graph generation model, the data collector generates a synthetic graph to estimate graph metrics. Obviously, this paradigm provides a general solution, as the synthetic graph can support different graph metric estimation. However, it also suffers from low estimation accuracy. The second solution is, for each graph metric, designing a dedicated solution and then estimate that kind of graph metric. Different from the first one, this paradigm can achieve higher estimation accuracy, but cannot generalize such a dedicated solution to other problems. It works poorly or even no longer works if the target graph metric is changed. In the view of these two paradigms, solution generality and estimation accuracy seem to be a trade-off problem. Is it possible to achieve both of them? Motivated by this, we develop a framework to solve this problem. Then I will first introduce our building block, a promising privacy-preserving technique, that is local differential privacy. Always say LTP for short. Under LTP, each user locally perturbs her data before sending to an untrusted data collector. Randomized response has been the predominant technique for privacy guarantee of LTP. Specifically, when a user is asked, are you HIV positive? Surely, the answer could be yes or no. Then each user will give the true answer with probability p and an opposite answer with probability 1 minus p. A mechanism is set to satisfy epsilon LDP if the ratio of P and 1 minus P is bounded by e to the power of epsilon. Based on local differential privacy, there are two different privacy definitions depending on the privacy requirements. The first one is no LDP. Under this privacy definition, an adversary cannot infer with high confidence whether a node exists or not. The second one, called edge LDP, makes sure an adversary cannot infer whether an edge exists or not. As each node often links with several edges, no LDP provides a stronger privacy guarantee. However, it also suffers from low accuracy. On the contrary, Edge LDP provides higher accuracy, and its privacy guarantee suffices for many graph applications. So in this work, we adopt Edge LDP. For graph data, it can be represented as an adjacency matrix, and each node denotes the adjacency bit vector of a user node. To satisfy Edge LDP, a naive method is to randomize each bit of a user's adjacency bit vector by randomized response. If we set epsilon to 1, then for the Facebook dataset with about 4,000 nodes and 88,000 edges, there will be more than 4 million edges in the perturbed graph, while 98% of them are fake ones. So graph analysis results can only be too noisy to use. As aforementioned, many graph metrics can be derived by adjacency bit vector and node degree. Inspired by this, we propose to let each user send two parts of perturbed graph data to the collector, that is adjacency bit vector and node degree. This is our design principle. Here is the overview of our proposed framework for graph metric estimation with local differential privacy. It consists of 4 major steps. Then, before we dive into the details, I will first introduce a graph metric estimation task, and we'll take it as an example to illustrate the usage of this framework. That is clustering coefficient estimation. The derivation of clustering coefficient is like this. For node A in this graph, TA is the number of triangles incident to node A. TA is equal to 2 in this graph, right? Then dA is the degree of node A, which is equal to 4. So the clustering coefficient of node A is equal to 1/3. For clustering coefficient estimation task, we need to estimate the clustering coefficient of each node. Then I will show how to use our proposed framework to estimate clustering coefficient. The first step is graph metric reduction. The reduction outputs a mapping function from a target graph metric to the adjacency matrix and degree vector. For clustering coefficient, we can split its derivation into 2 parts, while the first item, Ti, can be calculated from the adjacency matrix, and the second item can be calculated from the node degree. The step 2 is about price budget allocation. Here, I want to leave it to the end of this framework and first introduce step 3 of graph data perturbation. For the adjacency bit vector perturbation with epsilon 1, we observe that edges existence will be perturbed and sent to a data collector twice. This is an example. For these two adjacency bit vectors, the second bit of user 1 and the first bit of the user 2 both indicates there is an edge between them. This requires to divide the price budget epsilon 1 into 2 parts, which may lead to extra noise. To address this problem, we propose RABV protocol for adjacency bit vector perturbation as shown in this figure. In this protocol, each user only needs to perturb and send half of his adjacency bit vector, and then the data collector can obtain the whole matrix by copying bits in symmetric positions. For node degree perturbation with epsilon 2, we propose to add Laplace noise to each node degree. In addition, as we can also derive a noisy degree from the perturbed adjacency bit vector, we propose to refine len 2 to get a more accurate one. This can be realized by using maximum likelihood estimation method. The rationale is shown in this figure, and the refined degree can be calculated by this derivation. After receiving all the perturbed data from users, the data collector can estimate the target graph metric by aggregation. As the perturbed adjacency matrix is biased, calibration may be also needed. To derive the calibration function, we need to find the mapping between the estimated and real values. For clustering coefficient, we observe that DI tilde is unbiased, but the TI tilde is biased. So according to randomized response, we can derive the calibration function like this. The final problem in this framework is to allocate the price budget between adjacency bit vector and node degree. Here we use alpha as the allocation percentage. To do so, epsilon 1, which is equal to alpha epsilon, is allocated to adjacency bit vector perturbation, and then the rest, denoted as epsilon 2, is allocated to node degree perturbation. Our objective is to find the optimal alpha that minimizes the distance between real graph metric and our estimation. Here we use L2 distance as the loss function. For this example, we have the real and estimated graph metric as this. By substituting all map parameters, we obtain the derivation of alpha as this. So far, 4 steps of this framework has been finished. Now we illustrate how to use this framework to protect Facebook user data from being exposed to Cambridge Analytica. Facebook API essentially controls how a third-party app accesses the data of each individual user. So to limit the access, Facebook API should have a new permission rule that only allows such app to access the perturbed adjacency bit vector and degree of a user's friend list. In the Cambridge Analytica case, the app is a personality test. So the app developer may choose structural similarity as the target graph metric. To estimate structural similarity, the app then implements step 1, 2, and 4 of this framework. On the user side, each user can grant access to this app for perturbed adjacency bit vector and node degree if with enough price budget. So the above solution is our answer to the Facebook privacy scandal. Here is our conclusion. We propose a framework for graph metric estimation with local differential privacy. To the best of our knowledge, this is the first work in this field. We provide parameterized algorithms for user-side perturbation and collector-side aggregation and calibration. Further, to improve the estimation accuracy, we also present an optimal solution to allocate the price budget between adjacency bit vector and node degree. That's all. Thank you.